Hey, I'm happy to be in the new class. Are you happy? Let's go. Good. Expansivity. Yeah, I'm sure this topic is most of us are not uh, just saying this. Expansivity is from the word expansion. Something expands. Three things happen. Now, it should be expansivity or expansion of solids. That's what I would have used. Expansion of solids. So if you have expansion of solids, expansion of solids, expansion of solids. Now, if you have that, three things can happen. The solids can expand either linearly in terms of length, it can expand area wise in terms of area, and can expand by volume. So what's the formula? There's something we call linear expansivity. It's like alpha is equal to the L2 minus your L1. Don't forget we did it in maths. The final length minus the initial length, which is also the same thing as extension, then upon your initial length, open bracket, change in temperature. It's change in theta, change in temperature. The same thing goes for area expansivity is denoted by beta. Area expansivity is denoted by beta, that is A2 minus your A1 in the final area, the new area minus the initial area divided by what? The initial area times the change in temperature. The same thing goes for what? Volume expansivity, which is also noted as what? The volume expansivity is noted as gamma, and that is what? V2 minus V1 upon V1, open bracket, your change in theta. So this is exactly what this topic is about. Apart from your apparent expansivity and the rest of that, we'll talk about that in the next video. So this is just for expansion of solids. What happens when a solid material expands is either the expansion is related to the length of the body or the area of the body or the volume of the body. So quickly, let's get down to business by solving these questions. And you should know the relationship between each of these expansivities. Your linear expansivity has a relationship with the area expansivity and the cubic expansivity. We also talk about that. Let's get to business on the question we have before us. So what did we have? Look at what we have here. We have it that a brass rod is 2 meters long. I will take that as L1. 2 meters long at a certain temperature. At a certain temperature, that temperature is not given. They say calculate the linear expansion. Alpha is what we are looking for. Of the rod for a temperature change. They've given us the change in temperature. They did not give us T2. Don't forget, change in temperature is also T2 minus T1. But now they have given us already to be 100 Kelvin. Are you seeing that? Yes. A rod is 2 meters long at a certain temperature. Calculate the linear expansion of the rod at a certain temperature. Okay, if the linear expansivity is this. The linear expansivity is already given. So the next question will now be, how do we go about this question? How can we solve a question that is of this form? So quickly, without much ado, we've written out our parameters. But I don't know if you are seeing a brass rod is 2 meters long at a certain temperature. Calculate the linear expansivity of the rod for a temperature change. Okay, take this to be this. We are calculating the linear expansion. The linear expansion. Yeah. Calculate the linear expansion. That is not linear expansivity. They've given us linear expansivity. Linear expansion is what? L2 minus L1. And that is like the extension. So that's what we are looking for. But before we can get L2 minus L1, we must get L2. Yes, we must get L2. Now, our alpha has been given, the linear expansivity is 1.8 times 10 raised to power minus 5 per Kelvin. Can we move on? Please also note your temperature should be in Kelvin. It's not in Kelvin, it's in degrees Celsius. Add it to 273 Kelvin, you'll get a value in Kelvin. So let's solve. Let me wipe this and solve. So we have this. So we have this. The formula says that alpha is equal to, we've written that. So let me just write it. That's linear expansivity. That's 1.8 times 10 raised to the power minus 5 will be equal to, my L2 is what I don't know, minus L1. L1 is 2. So let me write it straight up. 2 divided by 2, open bracket what? Change in temperature, which is 100. Am I good to go? Yeah. So I have, you can, because you're looking for L2, so you have, you cross multiply, you have L2 minus 2 can be equal to what? 200, which I can rewrite as 2 times 10 raised to the power 2, then times 1.8 times what? 10 raised to the power what? Minus 5. By law of indices, 10 raised to the power 2 times 10 raised to the power minus 5. Bring them together. What do you have? Multiply 2 times 1.8. What is 2 times 1.8? What will it give us? 2 times 1.8. So we have 3.6. 3.6 times 10 raised to the power what? Minus 3. Raised to the power 2 times raised to the power minus 5. By law of indices, add together, you have minus 3 left. So you have 3.6. So we have our L2 minus 2. So L2 can be equal to what? 3.6 raised to the power minus 3. That should be 0.00036. You can check 1, 2. Oh, that should be something is missing. So you have 3, 6 there. Do you see this? 3.6 times 10 to the power minus 3 will give you 0.0036. 1, 2, 3. Correct. Then this 2 is here. You add it to this. So your L2 becomes what? 2.0036. You get that? So L2 minus L1 can be equal to what? That is 2.00. You have 2.00. 2.006, 0036 rather, So 2.0036. Sorry, permission to trying to see what's going on. Then minus, what's our L1? Our L1 is 2. So L2 to subtract this, I'm going to be having 0.0036. What is in meters? So that is the linear expansion, which I can also call the extension. Am I good to go? So that is that about question 1. Let's move to the next question. So we have question 2. Question 2 says, a solid material of volume 100 centimeter cube. Oh, good. I think this is where I need to make that known, that a solid material, okay, let me read this. A solid material of volume 100 centimeter cube is heated through a temperature difference of 40 degrees Celsius. They've also given us the temperature. This when that is the what? The change in temperature they've given us. Calculate the increase in the volume of the material if its linear expansivity is 2 times 10 raised to the power minus 6 per Kelvin. We are dealing with what? Volume. And they are giving us linear expansivity. How do you go? You must know that the linear expansivity is equal to 2 times your area expansivity. Then the same linear expansivity is equal to what? 3. Oh, sorry about that. Area expansivity is equal to 2 alpha. That is 2 times the area linear expansivity. Then gamma is what? 3 times your linear expansivity. So this is what you're going to use here. You are giving us what? Linear expansivity, which is this. So to get your cubic expansivity, which is volume expansivity, we multiply it by 3. That means gamma should be equal to 3 times. What is the linear expansivity? The linear expansivity is 2 times 10 raised to the power minus 6. And that can be what? 6 times what? 10 raised to the power minus 6. So that's what our cubic expansivity would be. So we go now. Our cubic expansivity is this. You have 6. 10 raised to the power minus 6 can be equal. We are looking for what? Increase in the volume. Calculate the increase in the volume of the material. The same thing we did to question 1. We are looking for L2, V2 minus V1. And we are looking for. So V2 minus what our V1 is 100. 100 centimeter cube divided by 100 over what? Open bracket what? Change the temperature is 40. So this is what we'll do. 40 degrees Celsius. Change your degrees Celsius. Change it to Kelvin. That will be, to change to Kelvin, we're going to be having 273 plus 40. And that becomes what? 3, 11, 313. Don't forget also that if we decide to change this 100 cm cube to, okay, you can have this in meter cube, you can equally have it in dm cube, though 1 liter is already equals to 1 dm cube. Yes, so we may not actually have to do that. So you have v2 minus v1. So since you are changing, just calculating the change in volume, increase in the volume, so that's, you don't have problem. Calculate the increase in the volume. So you are looking for v2 minus v1. That's what you are looking for. So what do we do now? We multiply this. This becomes 313 times this. So you have 6 just 6 6 times 10 raised to the power of minus 6, then times 313 times 10 raised to the power 2. This can be equal to what? This can be equal to v2 minus 100. So if you have this to be v2 minus 100, what do you have? You move ahead, and what do you get? You get 6 times this. So you have 6 times 313. 313 times 6. That gives you 1878 times 10 raised to the power minus 6. Then times 2, that is raised to the power minus 4. And that can be equal to v2 minus 100. So v2 can be equal to what? 1.878 plus 100. So v2 can be equals to 101.878 centimeter, which means that v2 minus v1 can be equal to 101.878 minus 100, and that becomes what? 101.878 minus 100. That becomes what? 1.878 centimeter. So this is the increase in the volume of the solid material. Thank you for staying with me. See you again some other time. Goodbye.